Hello everyone. So today a very interesting question where we get free continuity of the inverse of a function. So suppose x and y are topological spaces. So this is the minimal assumption where we have a notion of continuity and x is compact. Prove that if f is a continuous function that is one-to-one, so that we can define an inverse map, set theoretically speaking, then this inverse function happens to be continuous. In other words, if your domain is compact, and as long as you can define an inverse, it will be continuous automatically, which is kind of surprising. So as for the proof, to show that a function is continuous, we have to show that the pre-image of every open set is open. But this is equivalent to showing that the pre-image of every closed set is closed. So to keep track of what map is going from where to where, suppose this is your x and this is your y. This is map f, and f inverse is going in this direction. So we must take a closed set in the image of f inverse. So that means you will take a closed set A inside x, and we have to show that the pre-image of f inverse of A, that is the set of points which f inverse maps to A. So here f inverse, the first -1 means the inverse of the function. The second one stands for the pre-image. That means the set of points in y such that f inverse of y belongs to A. So I'm going to show that if A is closed, then this pre-image is also closed, and that will show that f inverse is actually a continuous function. So the way we prove this is as follows. So fix A subset of x closed. Then because it's closed inside a compact set, it is also compact. So then A is compact. Because f is continuous, f of A is compact inside. So f A is sitting inside y. So in particular, fa is closed. But f of A, which is the set of y such that y equals f of x for some x in A, is exactly equal to the set of y's such that f inverse as a function of y belongs to A. Because then f inverse of y will be exactly that x, the unique one that f of x becomes equal to y. And this is exactly the f inverse's pre-image A. And that's the end of story. So we showed pre-image under the function f inverse of every closed set is closed. Again, because open sets are complements of open sets, this also shows that the pre-image of every open is open, and that means f is continuous. So that's a nifty proof there of this theorem, lemma, whatever you call it. But it's kind of so tricky, you don't really see the big picture and why this is happening. And the best way to see the depth of this theorem and also appreciate its usefulness is to come up with a counterexample. So we want to see a counterexample when x is not compact. Okay, so we want to find an example of an x, and an example of a y and a continuous function f. So that is find f from x to y continuous and 1 to 1, so that f inverse going from y back to x is defined, but is not continuous. So to find such a counterexample, we ask what does not being continuous for f inverse means. So this would mean that there are very nearby points in y, so that f inverse maps them to faraway points in x. And if we go backward this way, so that means you have a, you have b, which are pretty far away, and then here you have x equal f of a and y equal f of b, which are pretty close. And then by looking at smaller neighborhoods, this problem cannot be mitigated, so that you keep having nearby points in y, so that f inverse separates them inside the metric space x. And to give you so how do you come up with a very specific example of such a map? Well, let's think about the simplest cases. So intervals are quite easy topological spaces. So if I reverse the picture above, it means there are far away points, so that f brings them close together. So here I want to find a here, and I want to find b here, so that in the image a and b get very close to one another. And that is literally saying that you wrap that interval back onto itself, and that produces a circle. So this will be my circle. Here will be f of a, and here will be my f of b. So that you see that a and b are far away, but in the image fa and fb are very close. So if you move a further closer to 0, and b moves further closer to this end, which for convenience I want to say is 2 pi, then fa and fb also will move closer to one another and to this point, which is 1, 0. And this is a subset of R2. And the map, if I give this map a formula, this is pretty specific enough, but if I really want to write a formula, this t is a real number here, and the map f will take t to e to power I t, I being the complex I. If you don't like complex numbers, then go with this cosine t sine t. So you can check that this f is obviously continuous. It has continuous coordinate functions, component functions. It is 1 to 1, interestingly. Well, it would fail to be 1 to 1 because right at 2 pi, it comes back to the same value as 0. But 2 pi itself is removed from my space x. So my space x is 0, 2 pi, but right when 1 to 1ness would fail, I have removed that trouble point. So technically, it is 1 to 1, but we know in essence, if we are fair, it is not. This passes all the tests. F is continuous. It's 1 to 1. And if inverse is not continuous, which we have pretty much discussed exactly why, and you can even write formulas. A and B are difference of A and B is pretty close to 2 pi, but difference of FA and FB is, say, delta, and you can make delta as tiny as you wish. So that counterexample shows you how important this theorem is with compactness. Just a little note in the end, if you wanted to do the same thing with a compact interval, let's see why it would fail. So you say you try to wrap, so you start here and you want to wrap it back here. But the point is, if this is 0 and if this is 2 pi and this is f of 0, then f of 2 pi, you have to assign a value to f of 2 pi. And in the previous example, you didn't have to assign a value to 2 pi because it was not in your domain. So you have to assign a value to f of 2 pi. And because you want injectivity, they cannot coincide. You cannot touch at these 2 points. And now because of compactness, not touching would put actually a buffer zone in between them. So not only they don't touch, they are also actually far apart by a positive distance. And that is why the inverse becomes continuous, because you cannot fix arbitrarily close points so that their pre-images are far away. Because if you take a very tiny delta, then delta neighborhood of this point only contains this branch and doesn't seep into the other branch. So I hope you like this lemma and you hopefully someday use it in a very nifty way, and also you see the importance of compactness through these counterexamples. So thank you for your attention today and have a wonderful day or night whenever you're watching this. Please subscribe to my channel if you have not yet.